We're going to use this figure from your book to go through an ECG once again, but also look at these drawings of the heart to see what the heart is doing at each of these 6 moments in time throughout a cardiac cycle. A couple things to make note. One, use your textbook. Your textbook has very good descriptions of each of these 6 steps. If you're not writing a bunch of notes down, you should be going to your book and reading through those 6 steps. Number 2, colors mean something in these drawings. Green represents when a muscle tissue is depolarizing. I'll remind you that depolarization is when the tissue cells become less negative. They're at rest when they're negatively charged. When they become less negatively charged, we call that depolarization. That is shown in green. Immediately after depolarization, muscle contracts. So whenever you see green, you should immediately see that chamber, whether it's the atria or the ventricles, contracting. Red represents repolarization. Repolarization is when that electrical current goes back to negative inside of the cells. When cells go back, when they repolarize back to negative, they're going to relax. A couple other words that might be new. When a muscle is in a contracted state, we call that systole. So atrial systole is when the atria are contracted. Diastole means relaxation. So when a chamber is in a relaxed state, we call that diastole. Like ventricular diastole is when the ventricles are relaxed. So let's begin. Point number 1. First, notice the heart. All the chambers are in diastole. They're all relaxed. The atria are relaxed, the ventricles are relaxed. The arrow represents the moment in time the pacemaker sends out its action potentials, or depolarization. From the pacemaker, or sinoatrial node, the action potentials spread throughout the atria and depolarize the atrial contractile fibers. I'll remind you where the pacemaker is located. It's located in the upper wall of the right atrium, and then that depolarization spreads throughout the atria. When the atria depolarize, we pick that up on an ECG as the P wave. While that P wave is being seen on an ECG, the atria begin their contraction. So right after depolarization, we see them in systole. Atrial systole is contraction. Notice that is occurring primarily at the end of the P wave, and after the P wave is when the atria contract. Next step is to send those action potentials from the atria to the AV node, down the bundle of His, to the bundle branches, into the Purkinje fibers of the ventricles, and then finally we depolarize the ventricular contractile fibers. That comes up as the QRS on an ECG. Notice in panel 3, the ventricles are beginning their depolarization, starting towards the apex and working their way up the ventricle in order to push blood up and out of the heart. At the same time, the atria are repolarizing. Now, you do not detect the atrial repolarization on an ECG, but you do detect the ventricular depolarization as the QRS. Immediately following the QRS, we note that the ventricles are now in systole. They have contracted. This is when blood will be ejected out from each ventricle. Left ventricle into the aorta, right ventricle into the pulmonary trunk. We then see the T wave on an ECG, and the T wave is representing the ventricular repolarization. So the ventricles have now turned red to represent repolarization. And immediately following the repolarization, we see that they have become relaxed, or said another way, they are in diastole, ventricular diastole or relaxation. Notice we're getting right back to the moment we started from, which is where all chambers are in their relaxed state. And we're going to learn later on that this is when a lot of the blood fills the atria and ventricles. And then we're right back to where we started. So again, keep in mind certain key points, like depolarization versus repolarization, like systole versus diastole, and then pay close attention to the waves on the ECG. So that's a normal ECG, that's a normal cardiac conduction pathway, that's a normal beating of a heart. Abnormalities of the electrical current we call arrhythmias. We're going to go over a number of arrhythmias, and it's very difficult to understand arrhythmias if you don't understand a normal EKG. So the first arrhythmias we're going to look at are called atrioventricular heart blocks. A heart block, as the name suggests, means that something is blocking the electrical transmission. And there's different severities. We're going to see that there's different degrees of heart blocks. The first one we call a first-degree heart block, or it's often known as a first-degree AV block, in that something is slowing up the conduction through the AV node. And when something slows that conduction up, what you see is an elongated interval. So there's a prolonged interval between the P wave and the QRS. We often call this a prolonged PR or PQ interval. So if we were looking at a normal EKG, this P wave would be much closer to that QRS. So when you see an elongated interval here, that often means something is blocking that transmission. That usually is a heart attack. So heart attacks will interfere with the conduction through the conduction system. But notice you're still getting QRSs, which is a good sign. A second-degree heart block is when some impulses are completely blocked at that AV node. And if you're completely blocked at that AV node, you never get to the ventricles during that cycle. Quite often you also see a progressive increase in the interval. So notice this first cycle appears fairly normal. The P is maybe a little bit far from the QRS, but notice in this next one it is longer and then even longer. So we learned that as a first degree. That PR interval has become elongated or prolonged. What makes this a second degree is during this cycle, there's a missed QRS and T. So there's the P wave. But right here, following a P wave should have been a QRS, and then there should have been a T, and then there's another cycle after. So when there's a missed beat or a dropped beat, we often call those second degree heart blocks. Third degree heart blocks are even more severe. This is when the bundle branches need to take over for the pacemaker. What happens is the pacemaker fires, but it can't get through the AV node. It's completely blocked each cycle. It sounds really, really bad, and it is. But your heart has come up with a mechanism to survive. So during these complete heart blocks, the bundle branches assume the pace and kind of take over. The problem is they don't do it exactly the same way, and it can lead to improper blood flow. I'm not going to ask you to identify a third degree heart block. I will ask you to identify a first and a second. The third can be fairly complicated, and what happens is the atrial contractions and the ventricular contractions are independent. They don't have anything to do with one another because there's a just complete block in between them. So there's no relationship between the P and the QRS. Next arrhythmias are atrial arrhythmias. As the name suggests, there's some problem with the atria. So for these, you really look at the P waves. And if there's rapid irregular P waves, then we call that atrial flutter. Often atrial flutter will become more severe and lead to what's called atrial fibrillation. Atrial fibrillation is the lack of P waves. So the atria are no longer being depolarized, and they lose their ability to contract. Sounds very severe. In the world of arrhythmias, it's not the most severe arrhythmia. There's many people that develop atrial fibrillation. And the reason why it's not as severe is you still are getting ventricular contractions, which is the most important part of the heart, are the pumping chambers, the ventricles. So atrial flutter, you see a lot of P waves. These are all extra P waves in here. Whereas in the atrial flutter, you're missing P waves. So there's no clear P wave before these QRSs. This is the T. Keep in mind, we don't want to confuse P and T. P is always before a QRS. T is always after the QRS. So in this arrhythmia, if we locate the QRS and look immediately before it, we do not see clear P waves. There's also some irregularity to the interval between QRSs. Notice how they're progressively getting closer together as we go through this tracing. Ventricular arrhythmias are the most severe. Again, ventricles are pumping blood, and when they're not functioning properly, that's a bad situation. Ventricular tachycardia is fast ventricular contractions. The ventricles depolarize at very high rates. We often call these PVCs, premature ventricular contractions. Tachycardia means fast. So these are fast ventricular contractions. It usually results in improper filling of the heart. So the heart doesn't have time to fill those ventricles properly. And this can lead to the most severe case, which is ventricular fibrillation. Ventricular fibrillation is when the ventricles have gone from full contracting ventricles to quivering ventricles. So notice in this tracing, it's going from a VTach into a VFib. These are a bunch of little QRSs, and the ventricles are just quivering. And when they quiver, they don't pump much blood at all. This is the situation where we would have to use a defibrillator to try to shock that heart back into a normal rhythm. There are some other arrhythmias called bundle branch blocks. We're not going to really look at those, but if one day you're in the ER or you're working for a cardiologist, you'll hear about bundle branch blocks. Again, a lot of these are caused by heart attacks. Bundle branch blocks, a lot of the blocks are disruptions in the cardiac conduction pathway due to the development of scar tissue. And then finally, a flat line is called asystole. Asystole means no contraction, no detectable electrical current seen using an ECG. So the next video, we're going to start to put everything together. We're going to talk about what's called the cardiac cycle. So that's all events that occur in a heartbeat. So we're going to add the ECG with blood flow, with opening and closing of heart valves. And this is where we have to have some knowledge going into this video. So I highly recommend doing your studying. Study your blood flow, study your chambers, study your valves, study your ECG, before you really get into this video.